Problem B1. Suppose a domino stands upright on a table. It has height h, thickness t, width w as shown below, and mass m. The domino is free to rotate about its edges, but will not slide across the table. Question A. Suppose we give the domino a sharp horizontal impulsive push with a total momentum p. Question 1. At what height h above the table is the impulse p required to topple the domino smallest? Question 2. What is the minimum value of p to topple the domino? Solutions. For the first question, we can write equation for minimum required angular momentum. Because push is straight horizontal and this domino rotates around down left corner, so we have angular momentum after this push will be p multiplied by h. And if we require to topple this domino by minimum angular momentum L means that if we increase height, we can decrease p. And the highest possible position for this point is small h. So it means that solution for question 1 is big H equals small h. So that's the answer for the first question. Second question. In the second question, we can use energy conservation. It means that if we push this domino with momentum p, we can add some kinetic energy. And this kinetic energy must be enough to overcome a change of potential energy for rotation. So we need to find what is the highest point for this domino and compare it to the initial height of center of mass. And that will be this potential energy change. Because initial height of center of mass is h over 2, and the final is the length of the half of diagonal of this domino, which is a square root from h square plus t square. So that will be total change of potential energy, and that must be equal to kinetic energy which we got from this initial push. This kinetic energy equal 1/2 L square over I, where L is angular momentum, which we got from this push, and I is moment of inertia of this domino around down left corner. Now we need to count this I. Using a parallel axis theorem, we can count this I. So that will be I0 plus mr square, where I0 that's a moment of inertia around center of mass, which is 1 over 12 h square plus t square, and r is distance from down left corner to the center of mass, which is 1/2 square root from h square plus t square. So that will be total I for this domino around this down left corner, which is 1/3 mh square plus t square. And the angular momentum equal p multiplied by h. Now we can insert all this angular momentum and also insert I to this formula. After that equalize delta u to delta k. And finally we got the result for minimum p. That will be this formula. And this is the answer for question 2 from part A. Question B. Next, imagine a long row of dominoes with equal spacing L between the nearest sides of any pair of adjacent dominoes, as shown above. When the domino topples, it collides with the next domino in a row. Imagine this collision to be completely inelastic. What fraction of the total kinetic energy is lost in the collision of the first domino with the second domino? Solution for question B. First of all, when the first domino touch the second domino, it will happen on height big H equal square root from small h square minus L square. And this first domino has now angle with a cosine theta equal L over H compared to vertical. Now when we have absolutely inelastic collision, it means that both points of this attachment, they have the same horizontal velocity. And now we can count this horizontal velocity using angular velocities for both dominoes. Suppose that right after collision, these dominoes have angular velocities omega-1 and omega-2 respectively. It means that for the second domino, we have horizontal speed of this point will be omega-2 multiplied by height of this point, which is square root from h square minus L square, because it's the vertical. And for the first domino, we have this horizontal speed equal omega-1 multiplied by height h and multiplied by sine theta, which is omega-1 multiplied by the same square root from h square minus L square. We see that both horizontal velocities equal to each other. It means that angular velocities equal to each other too. It means that after collision, both dominoes have omega-2 equal omega-1. It means that after collision, they have the same angular momentum, because they have the same moment of inertia and the same angular velocity. And because they have the same push with the same horizontal force, this force is horizontal because there are no friction between these dominoes. It means that if we have initial angular momentum for the first domino before collision, it will distribute some angular momentum to second domino, but it will lose the same angular momentum. So in total is the same. So it means that because they have the same angular momentum, it means that both dominoes have final angular momentum equal half of initial angular momentum for the first domino. And now, because total kinetic energy proportional to angular momentum square, we did half for the first domino, half for the second domino, and total kinetic energy will be half from initial. That's the answer for question B. Question C. After the collision, the dominoes rotate in such a way so that they always remain in contact. Assume that there is no friction between the dominoes and the first domino was given the smallest possible push such that it toppled. What is the minimum L such that the second domino will topple? You may work to lower non-trivial order in the angles through which the dominoes have rotated. Equivalently, you may approximate T and L much less than H. Solution for question C. First of all, we can include orientation of these dominoes using angles. Suppose that when we have left domino oriented like main diagonal vertical, we can count what is angle alpha between this diagonal and the vertical. And same thing for right domino, where we have angle this main diagonal and vertical, that's beta, and it's going to counterclockwise. And also we have angle phi, which is between diagonal and side of a domino. And now we can count what is the relation between alpha and beta when these dominoes touch to each other. Let's count the position for right up corner for left domino and the left up corner for right domino. Position for the upper right corner for left domino, x1 equal this expression, and for small angle, that's h multiplied by phi multiplied by alpha. and X position for up left corner right domino. That will be this expression, which is approximately H multiplied by phi minus beta, because this T multiplied by 1 minus cosine phi plus beta, that's a second order compared to the first member, H as sine phi minus beta. And the same thing we can talk about height of y coordinates. If we count only first order, we can neglect a second order and find that height is the same, that's approximately h for both corners. And because they are very close to each other, these top corners, and when one domino touch another domino, x1 approximately equal x2 in first order. So it means that initial distance between up right corner of left domino and the up left corner of right domino is L. And when we rotate left domino by angle alpha and right domino by angle beta in opposite side, we have this relation between alpha and beta. It means that alpha equal L over H minus beta. And this we have to memorize and use for next step. Next step is to find what is maximum potential energy when these two dominoes slides to each other after collision. Potential energy for the first domino when it's rotate angle alpha from vertical position is this one, and with approximation for second order, this one. And same thing for P2, for potential energy for the second domino. That's compared to bottom to the floor. And now we can add these two equations and find what is maximum for them using this relation. We take first derivative, use this relation, and finally find that the maximum potential energy will be for alpha maximum and beta maximum equal L over 2H. So we have to memorize this result for next step. Now we can use energy relation, and the energy we can count without all these coefficients, just using the common behavior of any functions near the maximum point. That will be this behavior. Suppose that if we have domino in vertical position, the potential energy equals 0. And in highest position, when diagonal is vertical, we have potential energy equal P. In that case, we can use this formula to approximate behavior for potential energy with the angle alpha for the direction of this diagonal. That will be a quadratic function for potential energy. And let's check. If we have alpha equal 0, we have a potential energy equal P, and if alpha equal phi, potential energy equal 0. So that's a true behavior. And the same thing we can say about right domino. Initial potential energy for initial position when left domino in vertical direction for diagonal and right domino in vertical position is P. Angle phi equal T over H. And also we can use angle psi, which is equal L over H. It means that when left domino just touch the right domino, alpha equal psi minus phi. And total potential energy difference between highest position and position when it touch the right domino will be this expression. And now all this potential energy go into kinetic energy when just before collision. And after collision we are losing half of this energy. So it means that we have a delta K of kinetic energy equal this one, half of delta P. And now we can write a relation for energies. Final potential energy when alpha maximum equal beta maximum, that will be this expression. Here we use alpha maximum equal beta maximum, and because L over H equal Psi, we can rewrite this formula. This is potential energy for both dominoes in the highest position for potential energy after collision, and that must be equal to initial energy right after collision. That will be initial potential energy, which is P, minus energy lost during collision, which is this expression. And now we can cancel P and do this equation. Now, after cancelling quadratic members from right and left side, and using a relation that Psi equal L over H and Phi equal T over H, we can find that critical L will be equal 3 over 2T. It means that if L less than this 3 over 2T, right domino will not flip over. If it's greater, that will flip over. So that's the solution for question C in problem B1. Question D. A row of toppling dominoes can be considered to have a propagation speed of the length L plus T divided by the time between successive collisions. When the first domino is given a minimal push, just large enough to topple a start chain reaction of toppling dominoes, the speed increases with each domino, but approaches an asymptotic speed v. Suppose there is a row of dominoes on another planet. These dominoes have the same density as the dominoes previously considered, but are twice as tall, wide and thick, and placed with the spacing of 2L between them. If this row of dominoes topples with the same asymptotic speed v previously found, what is the local gravitational acceleration on this planet? Solution for part D. This part is independent of the others and requires only dimensional analysis. The speed v can depend on g, h, w, l. To get a quantity with a dimension l t power -1, we must take v equal dimensionless coefficient multiplied by square root from g multiplied by l, where l is some length made from h, w and l on the new planet. V is the same and L is twice as much, so G must be half as great on the new planet. That was a solution for part D.